Hello friends, welcome to this video. In this video, we will delve into the fascinating world of GAN and specifically explore the implementation of DCGAN, that is Deep Convolutional Generative Adversarial Network. DCGAN is an extension of the traditional GAN architecture designed to enhance the generation of high quality images. DCGAN incorporate convolutional layer in both generator and the discriminator networks, providing several key advantages. These convolutional layer enable DCGANs to effectively capture spatial hierarchies and patterns in images, making them well suited for tasks like image generation and manipulation. We will start by taking a look at the dataset itself. The name of the dataset is anime faces, and I have used this dataset in my previous GAN videos. So if you haven't watched my previous videos, you can check the description. Now let's take a look at the samples from this dataset. So you can see multiple different anime faces, and all these images are resized to 64 by 64, and all these are PNG images. So this dataset contain about 21.5k images. So we will use this dataset for the implementation of DCGAN. So now we'll start with the coding part. So first of all, we are going to import all the libraries and the functionality we require for the implementation of our DCGAN. Here you can see we are using TensorFlow as our main library for the implementation of DCGAN, and the rest of the functions we will use to build our helper functions. Now we will have some constants, that is image height, image width, and the number of channel in our input images. And as you have already seen from the dataset, this is a specification. Now next we will have a function called create dir. So this function would help us to create some folders. Let's say if this specific path does not exist, it would create that path. Next we will have a function called load images. So this function would take a single image path. It would be an image path as a string. So first of all, it would read that path, then it would decode that PNG image. Basically it's going to read that PNG image, then we're going to change its data type to float 32. After that we are going to normalize the pixel value. So normally the range of pixel values are between 0 to 255, and with this line we're going to convert them in the range of -1 to +1, and then we're going to give this normalized image back. Okay, next we're going to have a function called tf underscore dataset. This function is used to build our training pipeline. So this function would take list of images path and a specified batch size. So first of all, we're going to take our images path and give it to the from tensor slices function, which is from the tf.data.dataset API. Next we're going to shuffle the dataset or the images path. After that we're going to use our load image function and read each individual images. After that we're going to create batches of images, and each batch contains a specific number of images that is specified in the value batch size. After that we're going to specify the prefetch. So what this prefetch does, let's say your batch number 1 is in training. Now this prefetch function would bring let's say batch number 2 and 3rd and 4th in a queue, so that when your batch number 1 is complete, it can simply give the batch number 2, so that there is no gap in between batch number 1 and 2. So this basically optimizes your training pipeline. Next we're going to implement our conv block, because we are working with a DCGAN now, and DCGAN uses convolution layer. So first of all, we will have our conv block functionality. So it take your x as the input, then number of filters. Number of filter basically refer to the number of output feature channels. Next is the kernel size, that is 4 by 4. Padding equals to same. Stride equals to 1. Then activation function, default value is true. So here we have our convolution layer with the specified values, and here you can see we have specified a kernel initializer of this, that is random normal with mean 0 and a standard deviation of 0.02. So you need to keep this specific value only. After that, if your activation function is true, we're gonna have a leaky relu and a dropout. Now again, you know why we use leaky relu? If you know, please comment it down. Okay, and let me tell you now why we use leaky relu instead of normal relu. Because in normal relu, we have dead neurons. That is, some of the feature map became 0. So to deal with that issue, we use leaky relu. And that is about the convolution block. Next, we have our deconvolutional block. So this deconvolution block is basically used to upsample the feature map. Let's say your feature map is of size 16 by 16. So it would convert it from 16 by 16 to 32 by 32. Again, we have our function with the name decon_block. It take x as your input, then the number of filter, basically number of output feature channels, then a kernel size of 5 by 5, padding same. So padding same means basically your that is the height and width of image would remain same. Let's say they are 16 by 16, it would become 32 by 32. So if you specify padding as valid, so it would change around, I think, to 31 by 31, and stride equals to 4. So this is the default value for the stride. So stride 4 means that we're going to upsample that image by factor of 4. After that, it is followed by, okay, next we have this cone 2D transpose layer. We have given the specific thing, and again here we have a kernel initializer with a random normal mean 0 and deviation 0.02. After that, it is followed by base normalization and a leaky relu. So these are about the basic blocks, that is con block and the decon block. Now we will move on to the implementation of generator. Okay, so now here we have our function name build_generator, and it would take a latent dimension. So this would be an integer value. So your generator would take a noise and give you a fake image. So here is our noise as our input. So first we would have a dense layer. Okay, and the size of that dense layer would be 4 into 4 by 512, and we set bias to false. So here you can see we have mentioned the specific size, because after that we're going to reshape it back to 4 by 4 to 512, so that we can have a spatial feature map which have a proper height and width. Okay, that's why you can change it accordingly. Okay, after this dense layer we have a base normalization and a leaky relu, and we reshape it. So now we have a spatial feature map. Next, it is then followed by the deconvolution block. So here we upsample it by factor of 2. You can see we have changed the stride value to 2. So we have 4 deconvolution layer. So you can see the size of the feature map we have given input is 4 by 4. So this x, the output of first decon block, would become 8 by 8, then 16 by 16. Then this x would be 32 by 32, and after that it became 64 by 64. And this 64 by 64 is same as the original height and width of the image. Okay, so now let's move back to our code, and after that we have a normal convolution layer. Okay, and here we have set activation to false, because we're going to change our activation function to 10h, and this 10h output of this 10h would act as a fake image. Okay, and we're going to build our model here. So that is about the generator. Now we'll move on to the discriminator. So discriminator is simple. It's just a classification architecture which is help you to discriminate between a real image and a fake image. So we're gonna give an image to this discriminator. It can be real or fake. After that, it is followed by 4 convolution block. Okay, and these are the number of features for each convolution block. And after the 4th convolution block, we're going to flatten the feature map and have a dense layer with 1 as the number of features, and we get our model. So discriminator is simple. Just need to make sure that both the discriminator and the generator are equal in size, so that one cannot dominate another in terms of its power. Now we'll move on to the training function. Okay, so this is our training function called train underscore step. So this function basically represents the functionality that happen within a single epoch. So it take first of all real images, okay, then latent dimension, then generator architecture, the discriminator architecture, then optimizer for both generator and the discriminator. So first of all, we need the specific value for the batch size, because every computation happening here would be in batches. So we need a specified batch size, and that we get from our real images. Okay. And next we have our loss. So our loss would be binary cross entropy. And here we can see we have set from log it equals to true. And we have applied a label smoothing of 0.1 to improve our performance. Okay. So first of all, we're going to train our discriminator. So first of all, we have an initial noise. Okay. You know, we give noise to the generator as an input and we get a fake image. Okay. So now we have a loop. So this means this loop basically says that we're going to train the discriminator thrice as compared to generator. Okay, and the reason is very simple. We want our discriminator to be a bit stronger than generator, so it forces the generator to generate more realistic images, because a powerful discriminator would easily discriminate between fake and real images. And if it can easily discriminate that this image is fake, so it would force the generator to generate more realistic images. So that is why you can play with this number yourself. Maybe first of all you can train both the discriminator and generator same for few experiments, and then you can play with this value and see. And if you have any information from this, if you get any anything from this experiment by playing with this and the number, how many times you're going to train the generator, please comment it down and do let me also know, because I am also studying GANs. Okay, so now let's get into the functionality. So first of all, we have our generator. We give it the noise and we get the fake images or generated images. Now we have a set of real images and a set of generated images. Now we give both of them to the discriminator and we get a real output and a fake output. Okay, so these are the predictions of the discriminator when give them real images and when we give them generated images. So now we're going to train the discriminator here using our BC loss. So for these we also going to need the ground truth. So in our loss function, first we give real output. Okay, this is the prediction for the real images, so its ground truth value would be 1. Okay, so let's say this is a list of, let's say, 10 values. It can be any value. Now this real output, that is the ground truth for this real underscore output variable, should also have 10 values. So that's why we say tf dot once like, and we give this tensor as the input here. So it would create an exact same tensor, just that all the values in the tensors would be 1. And same we're going to do with our fake output. We again use tf dot zeros alike and give fake output as the tensor. So this function would create exact same tensor as a fake output in terms of height and width, just that all its value would be 0. Simple terms we can say the ground truth for real output is a 1 and the ground truth for fake output is a 0 in discriminator. Then we sum both the losses and here we get our gradient and we apply them. So this is the process of training a discriminator. Now let's move on to the generator. So again we give our noise to the generator neural network and we get some generated images or fake images, and we give these fake images or generated images to the discriminator. Now we have fake output. Now we'll calculate our generator loss. So we again use our binary cross entropy loss and we give fake output. So this time remember these are fake output. So our ground truth here would be a value 1. can see tf dot once like and fake output. So what we are trying to say here is that we are trying to make the generator believe these are real images, and we calculate the gradient with the help of loss function and we apply those gradient. Okay, so this is about the training process, which is really essential. I think you should play with this and let me know if you have any query or if you get any information from it. Now next we have a function called save plot. So we give this function some examples, basically some prediction or some fake images, an epoch number and how many images, because it would save images in the form of a square, let's say 10 by 10. So this n would, if this n is 10, so this means it would generate 100 by 10 by 10 images, that is a square. Next we're going to move on to the training part. So we'll define our main function and then some hyperparameters. So first is the batch size, that is 128. So my system has an RTX 3090 which has 24 GB memory, so I can accommodate this size. Maybe you don't have that much powerful, or maybe you have GPU better than mine, so you can play with this batch number accordingly. Next we have latent dimension, that is 128, and samples, that is 100. So this 100 means you can see this value n, which is 10 if we specify. So this 100 is basically 10 into 10. So these many samples we want to generate. So this is basically should be a proper square, that is 10 into 10 100 or 9 into 9 81, something like that. Next we have number of epoch, that is 1000. So this is just a default value. I usually stops in between because the model trains nearly about 100 epochs is also enough to get some realistic, not properly realistic, but some realistic images. Next we need the data set. So we're going to load all the images. So I'm going to change the path here. Now let me run this architecture. Okay, so here you can see we have 21.5k images around. Now we're going to use our create dir function to create two folders. So first folder is samples. So in this sample folder we're going to save all the fake images that are generated after each epoch. Next folder is saved underscore model, and in this folder we're going to save the weight file of both generator and the discriminator. Next we're going to build both the generator and the discriminator model. So let me run this now and check if both the folders are created and see the summary of both. First of all, can see we have two folders, samples and save model, and these are blank now. And here you can see the summary of the generator and number of parameter. And I think when we use convolution layer as compared to dense layer in the vanilla GAN, the number of parameter are really less, because convolution layer shear weight, that is that kernel part, and this is our discriminator. So just compare the number of total number of parameter here. Okay, so we can see our discriminator a bit not, they don't have the same power, but still we're going to train it like this. Maybe you can increase this later. You should play with this number, I think, because I'm not an expert here. I'm not going to say everything I'm doing is right. So you should play with yourself and learn from your own experience, and please do share that experience also. Even if and I should also learn from your experience. Okay, so next we define the optimizer for the discriminator and for the generator, and they both have same value. So don't use same optimizer for both, use a different optimizer for both. Next we use our tf underscore dataset. We give it images path, list of all the images, and the specific batch size. Next we create a seed or the random noise, an initial random noise with a specific size, that is number of sample, that is 100, and the latent dimension. Now we'll go on to the training process. Okay, so we have a loop, for loop here, and it would iterate number of epochs time, that is 1000 time. So we start a time here to calculate how much time each epoch take. Then we have two variable here to keep the value of d loss and the g loss, that is discriminator loss and the generator loss. Now we loop over the images data set, and with each iteration we get a batch of image. We give this image batch latent dimension and other thing to the train step function, and we get the batch loss for the discriminator and the generator, and we add this batch loss to the d loss and the g loss. And after the loop is over, the first loop of this image data set, we calculate the mean discriminator loss and the generator loss. After that we save the weight files. Then we use our seed, this initial seed. So now we can see this is before the loop, so this seed value would not change. Okay, so now we give the seed value and we get our prediction. So here we have the example, and now we use our save plot. These are the examples, that is generated fake image, the epoch, and the square root of this number, that is 10. So this, it would be 10. So that is why I'm saying you should use a proper square. So that is 10 into 10 is 100. Okay, and here we calculate how much time it take, and then you print all the required values. So this is basically the entire program. It's about nearly 200 lines. So let me train it now and see what do we get. Okay, a lot of messages from TensorFlow. So let's see. Let's wait, and maybe till that time we can work on the test. So test is really simple. First of all, we load all the necessary libraries. Then we load the save plot function. Again, this is the same function, just that the epoch is not there, because there we use epoch in the naming scheme, but here we don't. Now we move on to our main function. So in main function, we load the generator neural network. Then we have number of samples we want to generate, latent dimension. Just make sure the value of your latent dimension do not change. Let's say in training you specify it at 128. Okay, in testing also you should specify the same. Then we generate some random latent point as the noise. Okay, and we give that noise to our generator, and we get some example, and then we save those examples. So this is about the test file. I think it's really simple. Okay, so you can see it's training. Let me show you the first. Okay, here is the first epoch. It took around 35 seconds. This is the discriminator loss, and this is the generator loss, and this is the second epoch. This second epoch, and now we have the third epoch. Okay, so training is being done. Let's check the samples. Okay, you can see 10 by 10 images. They all look same now, but just wait for a few more epochs. Now you can see the difference between them. So one thing for sure is that it's tried to generate some anime faces. You can see this is face here and the eyes. Okay, so it's really working. So let me stop it, and I'll replace the weight files. Okay, so that we can see. Let me delete those two folders. I already have the weight files here. So we have the samples here, we have the weight file here. So let me just run the test file, and I hope we do not get any error, because in the previous video I got an error and I don't know why. Okay, so we don't have any error now, and it runs successful. So you can see a fake sample, and these images look really well when I compared them to our traditional GAN images. So now the samples, we need the real. See, now just compare them. You can see these images a bit upsampled, and I compare with them. I think they look really nice, because they resembles the real faces. Some of them, if you see closely, may not look that well. So you can train it more, increase the power of the GAN or that is the GAN, the complete architecture, and train it more for more epoch on more data sets. So it would definitely improve. This is just a small demo. So how you can play with the GAN. So I hope you learn something from this video, and if you find this useful, then please do like this video, share it, and subscribe to my channel for more such video. Thank you. Have a nice day.